So we're passing out this simple orbit transfer tutorial. And this one, I don't usually talk through because I'm tired of talking by this point, but we're going to pass out the tutorial. The folks online can open up the user guide and go to page 60. The simple orbit transfer tutorial. And I promised lunch at 12, so we'll just take half an hour, go through the tutorial on your own time. And if you have any questions, let me know. I will give a brief just intro to it though. What we're doing here is designing a home and transfer. So we're actually going to use GMAT's targeting functionality to not only simulate an orbit, but design a maneuver to achieve a certain condition. So the problem here is that we have, let's see, we have Earth. And we're in this orbit about Earth. It's supposed to be circular. And we want to get out to another orbit. So this we'll call Leo. This we'll call Geo. And it turns out that theoretically the optimal way to get from Leo to Geo, or two circular orbits of any radius actually, is to start here at perigee, pretend this is perigee, and perform a home and transfer trajectory out to your other circular orbit. Sorry, it's not perigee because they're both circular. You start on the circular orbit, perform a 180-degree transfer from one to the other, and that will give you the optimal fuel usage case. So the tutorial has you start here, design this transfer orbit, and end up in this geo. So I'll do it on the screen just on my own time, but go ahead and go for it.
Do you want to mention that we should start with default?
Yeah, make sure, that's a good point. If you have GMAT up, either close it and reopen it, or click this this default mission button to get back to a clean state. I'll say for folks on the phone, I'll come back in about 10 minutes before 12 and wrap up a little bit, and then we'll break for an hour.
That he won't be able to come in regularly because he has other things to do. So if you don't want to know,
He can. Well, I sent him a thing saying he can call me if he wants.
Okay, yeah. He said that you still have to accept the request.
I just did like a minute ago. So if he calls me, I'll just leave it up.
You might be on.
Okay. All right, let me just break in here and describe what we did, so we can make it out at 12 for lunch, which I know is important. So what we basically did was we used GMAT to calculate the maneuvers required for a home and transfer. And the way we did that was by using a GMAT targeting sequence. So looking at the mission sequence here, we created a propagate command to propagate to periapsis of our low Earth orbit, which is slightly non-circular, which is why we have a periapsis. Then we created a target sequence that can be used to solve for the value of a parameter to achieve another value. Okay, so what are we varying? Well, we have two commands that vary. One, we're varying the magnitude of our transfer orbit injection, TOI burn. We perform the burn, propagate to the apoapsis of the transfer orbit, and then we test. So here's the test. We test that we have achieved a radius magnitude of 42,165 kilometers. Okay. So this is the first sort of set. Here's the second set. We then vary our geostationary orbit insertion burn, apply it, and we're achieving an eccentricity of 0.005. Of 005. Now, the reason why this is only 3 commands and the top one is 4 commands, we don't actually have to propagate in the geostationary orbit to make sure that we have an eccentricity of 0.005. We just perform the burn, ask it what eccentricity did I achieve, and perform the test at that point. So no propagation is necessary there. And then at the end, we have a propagation to go 1 day just to make sure visually that we've done the right thing. So if you run this out, what you'll see is that we start in our low Earth orbit. You're going to see these green targeting iterations appear, and you'll be able to watch the targeter progress the transfer orbit outward until it achieves what we asked it to achieve. So this is going to go sort of fast, but when you do it on your own computer, you'll see the green trajectories appearing and then disappearing. These are what the targeter is trying in order to achieve what we asked, which was this outer orbit. Now, one thing we can do that's a little added bit, we can go here into the default orbit view. So I'm opening default orbit view right here. And there's a option at the bottom called solver iterations. Okay, solver iterations. So this controls what iterations are displayed in the graphics window as it's performing the solution. So I have 3 options. I can show all of them, just the current one, or none of them. Right now it's set to current. I can change it to all. And what you'll see is when I rerun the mission, now all those solver iterations will stay around. And I can see that the targeter is progressing outwards in terms of achieved apogee until it finally gets a solution that's good, and it accepts that solution. So you can actually look here in the message window at the bottom to see all the details. Looks like it took 7 iterations, and it prints the final values here. A transfer orbit maneuver of 2.2 kilometers per second, a final maneuver, a second maneuver of 1.4 kilometers per second, which are realistic and typical for a geostationary transfer. Now one additional thing, and I'll show it because it's new in this release. I can change the colors of each of these segments so you can actually see where the burns occur. So the way we do that is we change the color on each propagation. So I'll leave the first propagation as it is, and I'll go to the propagation command for the transfer. And there's this box here that says override the color for this segment, and you can choose a color. So what I'll do is I'll override the color. I'll pick a green, and I'll choose the second propagate, or the third final propagate, and I'll make that sort of a magenta sort of color. Now if you view the script for this, you'll see what that did. It basically added an orbit color syntax element here. So here's our stopping condition, and we added orbit color equals, this is just an RGB value, or you can put in quotes the color blue or whatever you want there. Now if I run it out, notice I have to hit run again because I've changed the mission. I'm not doing this live with the graphics, I'm changing the mission, rerunning it through. And I get sort of this easier to understand picture where it's clear that a maneuver happens right here and a maneuver happens right here. Now what if you wanted to do this in a script instead of in the graphical interface? Here's how you do it. Okay, so I start by creating my spacecraft and my propagator. Add our differential corrector for the targeting sequence. And I set up my orbit view. So this is sort of the minimal set of lines that it takes to set up an orbit view. We have, here's our solver iterations. We're plotting the spacecraft and the Earth. And here's our camera definition. Create our 2 burns. And that's the end of the resource configuration. Now we go to the mission sequence. Here's our initial propagate to periapsis. Add our target sequence. We'll fill that in a minute. And then do our final propagation for 1 day. Now looking here at this target sequence, just to blow it up a little bit, and then we'll fill in the values. So the first thing we're doing again is varying the first burn. So we put in a vary statement and the associated achieve statement. So we're varying element 1, which is the velocity direction. We're achieving radius magnitude. And then we need to actually apply that. So this line changes the value of the burn. We actually have to apply the burn, which is something that people often forget. Then we need to propagate to apogee of that transfer orbit in order to test that we've achieved the right magnitude. Now, somebody might ask, well, could you not propagate? Could you just immediately do the burn and then test what's my radius of apogee? You could do that, but it wouldn't be exact. We're using a beyond 2-body force model. So it'll get you close, but not exactly right. And then for our second test, second burn, we have a vary on the second burn, and we're achieving our eccentricity value. Now for this case, again, because we varied our maneuver, we have to actually perform it. But no propagation is needed because in this case we are just testing the two-body value of eccentricity. And that's it. Pretty simple. Any questions before we break for lunch?
Could you quickly run over how you kept the iterations showing up in the graphic?
Yeah. Let's see. So, yep, I just opened up the orbit view. You have that part? Orbit view definition?
Yeah.
Okay. And then over here on the right, the bottom right side, bottom left side, sorry, this drop-down box. Yep.
Okay, thanks.
So current will show the active one, and then it'll disappear, and it'll show the next one. That'll disappear, it'll show the next one. All will show all of them accumulating, and none if you just don't care. You want to see the final solution. All right, great. So this afternoon, we're going to come back at 1, and Rizwan, are you first, Rizwan?
Yeah.
So Rizwan's going to do a Earth to Mars transfer example where he's targeting the B-plane, Mars B-plane. You'll describe what all that means. And then after that, Steve Cooley, who's a senior engineer in our branch, will come in and describe how to model finite burn. So we'll target a maneuver using finite duration burns instead of impulsive. And then the end of this afternoon, we'll do a highly complex, well, a more complex optimization example. Great. All right. So I'm going to break for lunch for an hour. See you back at 1. And I'm going to pause the WebEx here and mute the phone. So I'll talk to you guys in an hour. Thanks.
To enable the plugins is just uncommenting the pound sign restart.
And restart. Yeah, that's it. Unless it's like MATLAB or something that needs some extra configuration.
Just in case somebody had propagated that for longer than 1 day, you'd see that you're in geosync, you're drifting westward. So I don't know if it's something you want to change to instead of targeting on the eccentricity, target on orbit period, and then you put in the
Oh, true. Orbit period,
86164. That's geosync orbit period. So.
Okay. Yeah.
Okay.
So
So I happened to target it for longer than 1 day, and said, "Oh, it's drifting westward." So.
Let me just see that. Oh, in the orbit, we're going around.
Yeah. If you look at it Earth fixed, or if you look at it on the ground track, you see it. You see the figure 8 drifting westward.
Huh. Yeah, you're right. It would be easier just to target on 86400 period.
No, 86164 because it's not 24-hour day. It's Sidereal day.
Oh, interesting.
So the geosync orbit period isn't exactly one
Okay.
calendar day or one 24-hour day.
Oh, that's interesting. So I'm gonna do that and then do the ground track.
Yeah.
So what, 5 days or something?
Yeah. Do it as is.
Oh, yeah. Yeah.
Okay.
We don't have a figure 8 like we expect.
Well, yeah. Well, I mean, you do have a figure 8. It's just
Precessing.
it's drifting westward. Yeah.
Cool,
So,
thanks.
Yep.
I assume this is the solution. This one.
Actually, the green, the darker color, the cheap green is all the sponsorship is going red. That's something that's a little application, and the solution cheap color, the sponsorship gray, the sponsorship would be actually some it's that something like that. Orange one, so they sometimes run a couple into it. So you want to mark the true or
That's what happens.
Yeah, but you can turn that off and then always get orange.
Right. Thanks.
So how would you determine, besides using the eclipse report, how would you determine if you were in light or dark? Is there built-in function?
Well,
I have to write my own.
It's a pretty simple equation. We have built in, you can ask for what the state of the sun with respect to your spacecraft. And then I think it's a couple lines to figure out if the Earth is in between there. You just have to calculate two angles and then compare them.
Right. Okay.
But yeah, you just write that in your script. I don't know what it is off the top of my head.
Yeah.
The harder problem is people want to generate an eclipse report that finds the exact time that you enter and exit, not just a true false, am I in there right now?
Sure.
So that's sort of what we're working on right now, trying to put that in.
Yeah. So this will actually be a base.
I think we have built in that because SRP needs to know if you're in shadow or not
Yeah.
to apply the force.
Right.
So we do a calculation inside, we just haven't exposed it through a parameter yet.
Can I ask you a question?
Sure.
When I run the animation,
Otherwise, if you
the burn, and then it starts doing the iterations. It throws it twice, the same iteration twice.
Yeah, it's doing perturbations. So the way that the differential corrector works, it
yeah, exactly, yeah. And
tries an initial guess
I
and
know
then
something.
perturbs it slightly. It's like there's a factor you can figure for what the perturbation is. And it just does that to calculate the sensitivity.
Yeah, so that's.
And then once it has a sensitivity, then it takes a big jump.
And actually, I was,
And then it does perturbations, and then it's a big jump. That's what, yeah, I think that's why you see 3. Is it 3 for every one?
That's 2 for everyone.
But as we say, we usually do little rules for ace, because After it passes certain threshold.
They do smaller belts.
But that one did too,
Yeah, after every, on average, it's every 2 to 3 months. Couple of gaps. The smallest one was around half the gap, and the longest one was 2.5 months.
So they don't let it get
Yeah,
to the point where it's.
yeah, they won't, yeah.
So,
That's
alright, so
cool.
Yeah, and you'll see that that's the motorcycle, that can work.
Yeah.
That's on the cedar. That's the
you go
one.
no load, zero, no higher than.
And so I think it's supposed to be the transmission is that it's supposed to.
So it does this small little perturbation just to tease out how sensitive it is, and then it sizes its step anywhere from 0 up to 1.5.
Yeah, that's
So,
why.
yeah, you're seeing a couple of those perturbations on the side. I think it does a plus perturbation.
Yeah, so that's a pretty nice mission.
And then it fixes that one.
GMAT.
So that's the first one. Plus, so the period minus perturbation.
Yeah. If you see
So
the.
if I'm zooming really close to those tracks, I can see that there's like.
I think so, yeah. I don't know if it's,
So, yeah.
or if you increase that perturbation size.
Yep.
Thank you. But I was looking, I'm like, what are they doing?
It's,
Thank you.
and the way that it's drawn, like, that, you know, it's like, drawn very weirdly, right? It's not so bad. To actually make that,
Oh, your iteration.
no, actually, if you make that, coordinate system, point to, Earth moon very center, instead of crossing, Earth.
Yeah.
It's gonna.
Why?
Oh, yeah.
The reason is I think you have to take
Yeah.
around the race of the Earth moon system, as opposed to making sure that, locating that mission point, x-axis is passing the sun, so that you won't be like.
Yeah, like.
We have to make sure that it passes to the sun and also to Earth moon very center, not only to,
Oh,
I
okay.
think
You also change this drastically.
in this guy,
Yeah.
So that's very clear. It's still found it. Just,
The third one looks like it tries something very similar.
yeah.
Yeah, no,
Yep,
this-
sure.
this happened before.
Oh, really?
I don't know.
Yeah, we're getting a crash here, Joe.
Oh, really?
Yeah. Never resolved, the mission point station DB. You open up all the command systems?
I was getting that for one of them and then it stopped doing it after, yeah, so I was getting a little bit of that too.
Well, yeah, if I open up this guy, see that?
Yeah, I was getting something like that, it wasn't for that, so it was for the other, it was for the
Okay.
other.
Yeah, so we had that in the last training also when we were opening the user-defined command system, we were getting a crash.
Hang on a second.